we're just going to look at it in our video. So make it a point to go through this video, which covers lecture 4.5. So what are we looking at? We're looking at cost, supply, capacity conditions, returns to scale, cost efficiencies in the short and in the long run. That's basically the content that we're going to cover in our section. Let's get to it. So this first table is illustrating a cost which is called total constant cost. So a total constant cost remains fixed in the short run. So it doesn't change. If you look at the above table that is being illustrated right now, you see that your total constant cost remain 35, 35, 35. So your total constant cost are your fixed costs, and they are shown by a horizontal line in the graph below. Then there's also what you call your variable cost, which increase proportionately with an increase in output. So if your output is increasing, if you increase your output by 1 unit, we expect your total variable cost to also increase. So these increase proportionately with your output. Then if you put your total constant cost plus your total variable cost, that gives you your total cost. You can see in the table, for example, when our total constant cost is 35 and the total variable cost is 24, our total cost is 59. Then we look at the next line when our total constant cost is 35 and the total variable cost is 40, the total cost becomes 75. So that's how you calculate your total cost. Then the slide is illustrating what you call the graph for your variable cost. So if you remember from your mathematics in metric, the graph y equals to x, that is more or less like how total variable costs are, like a straight line which start at 0. So we can observe that when your output is 0, if you're not producing anything, you expect your variable cost to be also 0, total variable cost to be 0. As soon as you start producing, that's when your variable cost also increase. And from the graph, it can be seen that your total variable cost increase proportionately with your increase in output. So that is your total variable cost graph there. Then put together, that graph is your total cost graph. It is a total cost graph in the sense that, as you can see, it casts the cost axis at a certain point. So that point at the cost axis is your total constant cost. Because remember, your total constant cost, you have them even when you're producing zero output. So that's where your total cost graph starts where your total constant costs are, then increases upwards. So that part that is increasing upward from the total cost line is the total variable cost. So again, if you put your TC is equals to TCC plus TVC, TCC being total constant cost and TVC being your total variable cost. Then we have this graph, this table rather, a very important table. Sometimes we examine you this, so you have to know how you calculate the different variables that you see there. So we have a number of formulas there, one of them being your average constant cost. So your average constant cost, you take your total constant cost and you divide it by Q. So as we keep on producing, you expect your ACC to keep on decreasing because output keeps increasing, which is Q, while the total constant costs remain fixed. So you expect for each unit of output, this graph to go downwards. Then you have your average variable cost, where you take your total variable cost and you divide them by the output as well. So with your average variable cost, yeah, they increase in a manner depending on the rate of increase of your total variable cost. So you're just taking your total variable cost and you're dividing them by Q. Then you have your average total cost, which is TC divided by Q. Then you have your marginal cost, which is important, which is your change in total cost divided by change in Q. So this is almost similar to what we covered when we were doing your marginal output, where we said change in output over change in quantity. But for a marginal cost, it becomes change in total cost divided by change in output. So marginal, remember, is the additional. So in this case, marginal cost is the additional cost that we incur for producing 1 unit. So let's observe a few relationships that are denoted there in the slides. So I've already highlighted that your ACC decreases as your output increases, since you're increasing Q and TCC remains fixed. And AVC decreases as well. It reaches a minimum, then increases as well. So this is almost similar to what we covered when we're doing the relationship between marginal output and average output, to say that when AVC is decreasing, your ACC also is decreasing. Then your AVC reaches its minimum point before the ACC, then it increases. So there is a point of intersection whereby you say your AVC intersects the ATC at its minimum. Yeah, that's another thing that you need to know. Then ATC decreases, reaches a minimum, then increases again. Then we have marginal cost as well. So marginal cost decreases, reaches a minimum, then increases again. So this has to do with the law of diminishing marginal returns as well. So it is in a U-shaped, open-faced, upward-facing U-shaped graph. It decreases, reaches a minimum, then increases. You will see later on there is a graph which shows this ATC and the where it shows the marginal cost and the marginal output. You will see that they are mirror reflections of one another. So like I've already said, the AVC, ATC, MC curves are due to the law of diminishing marginal returns. That's why they are like that. They are U-shaped. So that is the slope of your average constant curve. So it is decreasing, as you can see. The more output you produce, the lesser your average constant cost become, because your shape, the numerator, which will be your total constant cost, remains fixed while you increase your output. So it will keep declining and declining as you produce more. Then you have your AVC. If you are producing your AVC decrease, they reach the minimum point only to increase again. So this is U-shaped because of the law of diminishing marginal returns, as I've already highlighted. So it is quite important to note the shape of the average variable cost. Then let's look at the next slide, which looks at the linkage between average efficiency and average cost. So efficiency is to do with the ease of production. So if our productivity is increasing, this overall reduces our average cost. And if our productivity decreases, it increases our unit cost. So your AVC is the price of the variable input divided by the average output. So if we assume that our price of input is fixed, increases in efficiency, AO, which is your average output, if it increases, this will result in a decrease in AVC. So assuming your numerator is fixed, which is your price per variable input, if you increase your denominator, which is your average output, due to increase in efficiency, your AVC overall will decrease. And the converse is true. If your average input efficiency, which is your average output, if it decreases, this increases AVC. So our average costs are at its minimum when AO is at its, your lowest average cost will be obtained when AO is at its maximum. I can see there's a certain minimum, but actually when your AO is at its maximum, that's when we will observe lowest average cost. So this shows us that there's an inverse relationship. If your if your AO is increasing, AVC is decreasing, and if your AO is decreasing, the AVC is increasing. So important things to note there. We'll observe in the next figure the relationship between AO and AVC. So from the next figure, when increases in average productivity, this results in a decrease in AVC, like I've already highlighted, and a decrease in AO result in result in an increase in AVC. So there's that relationship, that inverse relationship between AO and AVC. So this is how it looks like. So that's your AO and that's your AVC. So when your AVC is minimum, your average output is maximum. So they mirror image of one another. If we're to use the output axis as the reflector, you will see that the maximum point of the AO corresponds to the minimum point of the AVC, which emphasizes that inverse relationship. Then you have your marginal efficiency and cost. So marginal cost, like I've already highlighted when we're looking at that table, this table, your marginal cost is you take your change in total cost divided by your change in quantity. So I'll just use a small example to illustrate this. So you can see there, when your total cost change from 0 to 24 and your output increases by 1, it's 24 divided by 1, which gives us 24. Then when your total variable cost your total cost rather, they increase from 35 to 59, and your input is increasing by 1. Your marginal cost is 24 because 59 minus 35 divided by 1, that gives us 24. But when it increases to 75, 75 minus 59, that is 16, then you divide by a change in output, which is from 1 to 2, that gives you 16. So that is your marginal cost. It is the additional cost due to the extra unit. So it is important that you master these formulas and are able to calculate each line item as you might be examined for this calculation. So make sure you master these formulas. Now going back to where I was, which is here. Your MC, which is here. Your marginal cost is the additional variable cost. Your marginal cost is the addition to your total cost by change in output. So that is basically your MC. So there is a proof in your textbook, which is on page 135. So this proof shows us that there's an inverse relationship between MO and MC. In as much as we saw that there's an inverse relationship between your average output and average total cost, there is an inverse relationship. Yeah, this inverse relationship that we saw here, this one between AO and HGC. So as well, there's an inverse relationship that you will see in your textbook. It's an inverse relationship between MO and MC. If your marginal output is at its maximum, you expect your marginal cost to be at its minimum. So it's almost in a similar relationship between your AO and AVC. Make note of that. So on page 135 in your textbook, that's where you see the derivation of that relationship. All right. So a few things to note there. So you can see that when MC is decreasing in the graph, your AVC as well is falling and your ATC as well is falling. So your MC, it intersects your ATC at its minimum, which is 0.1 there, as you can see. Then you have your point of intersection as well with your AVC, which is 0.2. So the MC intersects the ATC and AVC. Both of them, they will be in their minimum. So even your AVC, which is 0.2, it will be at its minimum. Then your ATC, which is 0.1, will be at its minimum. And remember as well from the two graphs that we have seen, the AVC and MC are mirror reflections of the AO and MO graphs. Something to note there. Then you have cost efficiencies in the long run. So your cost efficiencies in the long run, that's where you talk about your economies of scale and your diseconomics of scale. They become important in this. So it is important to determine in the long run whether a firm is experiencing economies of scale and diseconomies of scale. So in order for us to come to this conclusion, we have to derive what is called a long run average cost function. So this long run average cost function you look at the minimum points, you join successive short run average cost curves to get your long run average cost curve. So you can see there your short run average cost curves. If you join them, their minimum points, that gives you the long run average cost curve. So the long run average cost curve is still decreasing when output is increasing. So here will be cost efficient. However, in the long run, when I encountering diseconomies of scale, your long run average cost will increase when our output is increasing. So that is when we become cost inefficient. There's also what you call the least cost principle. So the building block of that is the least cost principle, which is what we use to derive your long run average cost curve. So we have quantity Q1, which is the output of the least cost function. We are talking about the short run average cost curve AC1. Then if our output is at Q2, is the least cost function for your short run average cost curve M. Then if you link those least cost functions, like I said in the beginning, that gives you a long run average cost curve. So your long run average cost curve, you obtain it by linking the least cost functions of these different curves is AC1, and then a short run AASACM. If you link those minimum points, that gives you a long run average cost curve. So as well, you can look at it in that manner to see you have your different short run average cost curve, their minimum points, that gives you the long run average cost curve. So it is a U shape, right? So the decreasing part is due to economies of scale. So when it is decreasing your long run average cost curve, it means firms in that region are encountering economies of scale rather. Then those are to the left of those minimum points. So when we are going down, when the average long run average cost curve is decreasing, if from quantities Q1 to Q3, they will be experiencing what we call economies of scale. So these economies of scale are the lowering of cost due to an increase in output. Then we have the increasing part of your long run average cost curve, which is from Q3 to about Q4. So this is when we're experiencing these economies of scale. So if we are increasing production there, our unit costs are increasing. So these successive short run average cost curves are occurring to the right of the minimum points. Yeah, to the right, we are experiencing these economies of scale. Then to the left, we are encountering economies of scale. So a firm might have to re-engineer its total productivity to ensure that it lowers its long-run average cost curve. So that is process re-engineering that can be done by a firm to ensure that it reduces its long-run average cost curve after it has started to experience diseconomies of scale. Then finally, the application of the cost concepts. So we can look at the real labor cost, where we can look at the change in the nominal labor. Then we are deflating it by the corresponding changes in productivity. So you want to see in real terms how your cost of labor is. So the real labor cost, it is positive if the increase in the nominal wages is more than the increase in productivity, i.e., the cost that you're paying to your workers is more than what they are producing. Like the wages are increasing more than the cost than the productivity levels. So hence, this is a negative impact on the firm because the firm is paying more without a corresponding increase in productivity. So that is a negative impact on the firm. Then the negative labor cost is when the nominal wage increases at a lower percentage than the increase in productivity. So this means that we are paying less than the increase in productivity. So this is a good thing. It has a positive impact and makes the firm more competitive. Then you have your marginal revenue product, which is applied to determine the optimal usage of the labor. So you look at the additional sales revenue generated by utilizing one extra unit of labor. So as long as your marginal revenue product is greater than the cost of labor, it means you keep on employing workers until you reach a balance. So overall with your marginal revenue product, it works hand in hand with your real cost of labor. You want to make sure that if it's still benefiting you more to employ workers, you employ them up until a point where the MRP is equals to your real cost of labor. Then you have your real capital cost as well. So this is to do with the relative supply of capital, then the cost of capital as well. So also in this case, you can see, you can compare your marginal revenue productivity of your capital and look at the cost of your capital. And you keep on employing, you keep on utilizing more workers, you keep on utilizing rather more of your capital units as long as your MRP is greater than the machine cost. So that's one thing to note. Then you have your NPV, which is the future receipts of a firm, where you discount them at their present value. So the discount rate will probably be the cost of capital that you use here. So a positive NPV, it means the firm should continue with the project and this project is value adding to the firm, while a negative NPV means the firm should not proceed with this project. So those are some of the concepts that we have covered in this section. But this one, you don't normally test it, but it is important for you to master those changes and know these changes. So that is what we have covered today. So the important elements to remember, knowing what makes up a total cost, the shape of your total cost. These calculations, I repeat, are very important. Make sure you know how to calculate your average constant cost, HVC, ATC, and MC. So in a test setup, we might give you a table with missing information and you might need to complete it. So it becomes very important that you know how to derive those figures denoted there. Then the relationship between your AO and MO, your AO and AVC, very important to know that they are mirror images of one another along the output axis. Also, the relationship between MO and MC, very important to note that they are mirror images of one another along the output axis. Then we have our least cost principle, which we use to derive a long run average cost curve. Then we have the shape of our long run average cost curve, which is a U shape. So that is the important elements. Go through this video and make sure this coming week you consult so that you can understand some of these concepts. Otherwise, guys, do have a lovely day and look forward to seeing you consulting.